Yes. Priyadashini? See if someone has some doubt, you can unmute yourself. You can ask your doubt. Okay. Okay. Fine. Okay. See, you should go through your materials. Okay. Because I'm not the one who can make you understand at the first go itself. No one can do that particularly. You have to help yourself, not me. Okay. Fine. Okay. Then I'm moving on to today's class. Yes. Okay. Moving on. Today we will be continuing from the previous lectures. So yesterday there was an example we had just ended with. I think you must have solved it. It's very straightforward. You don't have to use any so different formulas like different expressions like your voltage divided biasing or design of an amplifier. No, nothing like that. You just want to use that expression AF is equal to A divided by 1 plus beta A, and you want to solve everything. And similarly, for here it is given as Ri and R naught, and what we have wrote is Zi and Z naught. Impedance or resistance, anything is okay. Okay. So in the place of Zi, you can put Ri, the value of Ri, and in the place of Z naught, you can put the value of R. Okay. So here, look at this question. Determine the voltage gain. Voltage gain for voltage series feedback. For voltage series feedback, having A is equal to for A is equal to minus 100, Ri is equal to 10 kilo ohm, Ri is input impedance, output impedance is 20 kilo ohm, and for feedback of beta is equal, what happens when beta is equal to minus 0.1? That is, you are taking very less, I mean 10% of your output. And what happens if you are feeding back 50% of your output to the input? So that is the question actually. So you can see first they have computed the voltage gain. That means the gain after introducing the beta. That means the feedback network, and the value of the gain is minus 9.09. And here in the part B, if you see, when I'm feeding back 50%, that means 0.5 minus 0.5 of the output. That means I get a voltage gain of minus 9.6. So there is a So this is these two things you want to consider now. Here, if you see, this part is for beta is equal to minus 0.1, and this is for beta is equal to 0.5. Okay, so you can really check both the answers. See, all the expressions are readily available with you. We have discussed all the expressions yesterday, particularly ZIF and ZOF. ZIF is input impedance with feedback, and ZOF is output impedance with the feedback. You really can see that this factor 1 plus AB, 1 plus beta A will be keep on repeating. So you don't have to remember anything. You just want to logically keep something to remember these things. Okay, fine. And ZIF here is Zi into 1 plus beta A, and when you compare the input impedance values, that will be if I am feeding only 10% of my output, feeding back only my 10% of my output, then I have a reasonable gain. That means from 100, from minus 100, I am almost going down to minus 10 only. Okay, actual gain is minus 100. But when you see after introducing the feedback of 10%, your gain is now reduced to minus 9. Whereas if I am feeding back 50% of my gain, 50%, that is 0.5 of the output, you could see the gain reduces to minus 2. Okay, from minus 100 it is reducing to minus 2. So just think, because of this feedback, you want to sacrifice the gain. You are sacrificing the gain, but gain is not the only thing that is required for an amplifier. So that's the thing we have to notice here. And you really can check the you really can check the other two things. That is the input here, 50%. This is for 10% and this is for 50%. The input impedance is higher. That is the input impedance is higher when the feedback ratio is beta is equal to minus 0.5. That is 50%. Okay. So this is the desired quantity for, this is the desired thing for an ideal amplifier. For an ideal amplifier, that means for a good amplifier, your input impedance has to be very high. So that can be achieved only by giving a large amount of feedback. So based on your requirement, your beta value will be varying. So in some cases, you may not require a very high impedance. So you may require a very high gain. So what you will do, you will regulate that beta accordingly. Okay. And last thing we have to infer here is the output impedance minus 1.82 kilo ohms here, and this is very low. That is in terms of kilo ohms. You should notice it is in terms of kilo ohms. The output impedance is in terms of kilo ohms. When I take a feedback ratio of 0.1, that is 10%. Whereas when I take a 50% feedback ratio, that means 0.5, that means 50% of the output is entering into the input. Then I have a very low output impedance. That means 394 ohms only, not kilo ohms. This is just ohms. Just look at the comparison of these two. I am using a different color. You can see the difference. So for an ideal amplifier, your output impedance should be near to 0. So by using a feedback ratio of 0.5, we could able to achieve this. The only thing we are sacrificing here is the gain. The gain reduction that is happening because of beta is equal to 0.5. So that is the point I'm trying to make here. This example is particularly to view that particular thing. Okay, I hope this should be fine. And I'm moving on to the next slide. Okay, one parameter yesterday we have discussed is the loop gain. Loop gain, I think you must have roughly gone through in your control system. The term A beta here. The term A beta in your expression is known as the loop gain. Here, since it is a negative feedback, you will be having a minus. The loop gain is actually minus A beta. Okay, so it is a negative product of gain and the feedback factor. Okay. Okay, moving on to next slide. So there are two factors. There are one important factor that we have to that actually the feedback amplifier concentrates. It's a reduction of this distortion. Okay, so one is frequency distortion. The frequency distortion is, so when the feedback element beta is consisting of the elements like resistor, capacitor, and inductor. Okay, if it is purely resistive, then we don't have anything, any capacitances there. Then it is independent of frequency. So whatever the dependency of your amplifier in the frequency, that will be reflecting in your feedback amplifier as well. So see, whenever I say the reduction in the frequency distortion, you must compare your actual amplifier with the amplifier with the feedback. Okay, what happens to this frequency distortion when I introduce a feedback? That's what this frequency distortion is about. Okay, so what happens is that so this frequency distortion will be discussed in detail in the upcoming session. Okay, so and this frequency distortion is considerably reduced on using the feedback network. Okay, we will we will explain this in detail with an expression in the coming session. Okay, and very less noise distortion and nonlinear distortion. These things are already discussed, but we have to see with the expression. That is something that will justify the advantages of the feedback, advantages of introducing the feedback in your system. Okay, and here you can see the noise and the nonlinear distortion. You can really check on that as your gain is inversely proportional to 1 plus A beta. As gain is inversely proportional, that is AF is equal to A divided by 1 plus A beta. A is actual gain, and because of introducing the feedback, we will be having A divided by 1 plus A beta. Now for the feedback system, that 1 divided by 1 plus A beta will be there. That's why the gain is inversely proportional to 1 plus A beta. So that not only decreases the gain, but it also reduces the noise term as well. So reducing the noise means reducing the nonlinear distortion as well. So in that way, we will be reducing the frequency distortion and noise and nonlinear distortion. Okay, so these are all some advantages of the feedback amplifiers. Okay. The next one is the desensitivity of gain. Okay, so desensitivity, the term may seem in a negative, it can be seen in a negative term, but it is the desensitivity of the gain should be very high. Okay, yeah, your gain should not vary at any time. Okay, if I'm taking an amplifier and it has some gain, okay, that gain should be like that only. The gain, if I'm taking an amplifier of gain 100, it should be 100 at any temperature or at any season or at any circumstances. The gain should be 100. So that means it is not sensitive; it is desensitivity of the gain. Okay. So for an amplifier to be good, it has to be desensitive. It has to be desensitive of the gain. The desensitivity of the gain is very high. Should be very high. Then only it is a very good amplifier. Okay. Now we are going to check what happens to this gain. What happens to the sensitivity of this gain when we introduce a feedback. Okay. That is what we are going to do in practical terms. Okay. First one is, what is the gain with feedback? It is nothing but AF is equal to A divided by 1 plus A beta. So we are going to differentiate this with respect to A. Just a simple derivation. You can just differentiate with respect to A on both sides. We'll be having that you can use U by V the whole dash. That is U by V the whole dash means U dash. You can use that mathematical differentiation. So I don't think it's very complicated. It's 12 standard max. Okay, you just apply the 12 standard max in that AF is equal to A divided by 1 plus A beta. Differentiate that equation with respect to A, so that you will be ending up with this expression. Yes. You will be ending up with this expression. Okay. Sorry. Okay, so you can see that it is 1 by 1 plus A beta. Okay, we will do some circus in this. As the final expression, we have DAF is equal to, that is DAF means it is a small change in the gain due to feedback. DA means small change in the gain, actual gain. Okay, gain of the amplifier. So DAF is equal to DA divided by 1 plus A beta the whole square. Dividing this equation by AF on both sides. These are the very basic steps. I mean, very elementary mathematics. That's why I'm not explaining so much on that. I'm not stressing so much on that. If you keep solving it by yourself, you can easily reach to the answer without memorizing anything. Okay, fine. And you can see DAF. The next step, we just took that. You can clearly see that we are just multiplying or dividing by AF on both sides, and now my equation will be changing to the equation that has been given here. So this equation we can write as DAF divided by AF is actually known as the fractional change in the amplification with feedback, and DA by A is the fractional change in the amplification without feedback. That means fractional change in the first part is fractional change in the amplification with the feedback, DAF by AF, and DA by A is nothing but fractional change in the amplification without feedback. Okay, so you can see that, and so what do you infer from this equation? This equation is, you can clearly see that this term DAF by AF, this term will be always less than, okay, that means fractional change in the amplification with feedback is always lesser than the fractional change in the amplification with feedback. Okay, that is what this gain is. This equation proves. So this means on introducing the feedback, on it highly robust against the sensitivity of the gain. The system is changing. Is anyone?
Why is very breaking?
Sounds breaking.
Sir, we can't see your screen. And
1 minute.
I think we have less connection.
You can see my screen. Yeah, 1 minute. Check on that.
Yes, sir, no we can see.
Okay, may I know for whom the problem was?
This is Arun, sir.
The problem, the voice.
Hello, sir.
Who is this?
Arun, sir.
Yeah, Arun, tell me, Arun.
Sir, before 2 minutes we can't see your screen and your voice is cracking. Now we can see.
It's breaking. Okay. Uh, 1 minute. Yeah, is it okay now?
Now the voice is okay, but screen is not displayed.
Yeah. I just cut the screen so that my bandwidth will be completely used for my voice. Okay, I'll share the window again.
It's fine.
Is it okay now? Guys? Yeah, can you hear me?
Yes, sir. Now we can hear you and can see the screen.
Yeah, Arun Karthik, am I audible now? If my voice is breaking now, is it okay?
It's better, sir.
Okay, or should I have to call again? Should I have to
No,
break this call and no problem, right? Yeah, please speak out. Can I carry on?
yes, sir. You can continue.
Yes. Yeah. Thank you. Okay, mute yourself. Okay. Yeah, 1 minute. I'll have some more. Okay. So I hope you don't have a problem with these equations. I'm just pressing through. You can clearly see that we are dividing by AF on both sides, and for AF here, for the AF here, we will be substituting AF is equal to, we will be substituting this equation, okay, in the next step, so that we will be having dAF by AF is equal to dA by 1 plus A beta the whole square into 1 by 1 plus A beta divided by A. And on further simplification, we have the sensitivity the DAF by AF is a fractional change in the amplification with feedback, and dA by A is fractional change in the amplification with feedback. So whatever the fractional change that is happening with the amplification for feedback, that will be very higher. When we compare the fractional change in the amplification with feedback system, because we have the term 1 by 1 plus A beta here in the right side. So your dAF by AF value will be always lesser than dA by A value. Okay, so that is the inference, main inference we are seeing here. Okay, on because of introducing the feedback in your amplifiers, the sensitivity of the gain is getting very reduced. So as you can see, the sensitivity is given by the expression that is being displayed now. I am just circling that with the laser pointer. You can see that it is nothing but 1 by 1 plus A beta, and D sensitivity is nothing but the inverse proportional of inverse of the sensitivity. So as the D sensitivity is higher, your amplifier is very stable. Okay, D sensitivity is higher, your amplifier is very stable. So that is the thing you want to have in your mind, because I don't want amplifier to move between if I'm having an amplifier with gain of 100 dB, I don't want my amplifier to change that gain to below 100 or above 100 dB. Okay, if I'm having a 100 dB amplifier, means it should be 100 dB for at any circumstances. So that can be obtained only by introducing the feedback. So that's the point I'm trying to make here. Okay, I'm moving on to the next slide. Yes, can I take up some questions on this? Do you have any doubts in this slide? If you have any doubts, unmute yourself. I will wait for 1 or 2 minutes. 1 minute, you just unmute yourself and you can ask your doubts in the slides if you have some. Okay, please go on. Don't think it is a silly doubts or anything. Okay, because we want to make this session a little lively. Yes. Yes. Okay. I'm moving on to the next slide. Can I? Okay, how many of you remember this? What is this diagram? Yes. What is this diagram? We have a plot here, right? What is it? Yes, you can respond. You can respond through text. Go on. Pujit Sai. Who else? Darshini, Pragati. Someone? What is that plot is? Yes, very good. RC coupled amplifier. Very good. I got a response. Okay. I think now I can continue. So you have an RC coupled amplifier and you had the frequency response there. Yeah, you have did this in your lab, if I am not wrong. Yes. If you see this, the x-axis is the frequency and the y-axis is the voltage gain in dBs. This is the one you have drawn in the Semilog sheet. So here you can see that. Yes, I can use a different thing. This part, I'm breaking this curve into two parts. If you see this response, this is high pass filter response. High pass filter response. And the right side part, this part is low pass filter response. So I hope you remember how your amplifier circuits look like. So you have a coupling capacitor. Divider biasing, you will be having a coupling capacitor on the input side and the output side, and one more capacitor is the bypass capacitor that will be connected in parallel with RE. Okay. Ultimately, if you see this, nothing but a RC coupled filter, or RC filter, RC low pass filter or a high pass filter. Okay. It will be the way it will your circuit will behave is based on the frequency of operation. Okay. The input frequency is very low. Your gain is very low. Here you can see the gain is very low, and in case if your input frequency is in some reasonably high range, you will be having a flat response. That means your output will be of some particular gain. Once you reach a very high frequency there, your gain will again reduce. I hope you remember this doing in the lab. So what is the impact? That is the normal amplifier. Okay, that is a normal amplifier you want to think of. Okay, so now what happens to this curve when I am introducing a feedback in it? Okay, what happens to this curve when I introduce a feedback in it? That's what we are going to discuss now. And for that, we are taking the cutoff frequencies. We know that AF is equal to A by 1 plus A beta, and the corresponding gain in the low here, this point is taken as F low. This point here, this is taken as the corresponding feedback gain at that particular point is given by AF low is equal to A low divided by 1 plus A low into beta. And in the mid range at this point, at this particular point, take some point in that flat curve. Right now I am taking approximately a midpoint, so it is mid-range frequency, and at the mid-range frequency with feedback, this is the gain. There's nothing. We are just including the low, whichever frequency we are dealing, a low or a mid-range frequency or a high frequency. We are including in the suffix of AF and A. Okay, that's what we are doing here. And finally, we have high frequency, that is at this point. What is the gain with feedback? Okay, so we have defined all those things. And when we take a low pass filter, as you know, the amplifier circuit is consist of a lot of RC combinations. So we have a high pass filter response at some frequency of input, at some input frequency, so that equivalent high pass filter is given in this in this picture here. And you can see that this is the lower cutoff frequency, so it is FL divided by F. I hope this equation is little familiar with you. Anyone? I need responses right now, so I have boxed one equation. I am trying to box one equation. Is this equation is familiar with you? I want to know that. Yes, I am expecting some text responses. Please go on. Yes. Yes, please. I need some responses. Yes. Anyone? See, you know or don't know, just type that. That is enough. It is not necessary that you want to know it. Yes, hello. Guys, I have boxed one equation. I am I am expecting your answer whether you know that equation or not, whether I have to explain about that equation or not. No means you don't know or I don't want to explain. Please let me know that. Please be clear with your answer, please. Pragati. Fine. Okay. So, okay. So, have you seen the what is the equation you have used for your low pass filter design when you are doing your last semester's lab, Anirudh sir lab, if I'm not wrong. There, if you see, we will be. See, I'm taking this. Fine. Okay, I'm taking this diagram, high pass filter. You can see that the output is taken from the across the resistor, and in your circuit you are having the capacitor. So my gain is actually V output by V input. Okay, V output by V input. Okay, V input, which is equal to, I am taking the output across my resistor. So my output voltage is equal to V output is equal to total voltage VI into R. Please mute yourself. Yes. Yes. Then you can see that the output frequency, the output voltage V output is equal to total input voltage VI into R divided by R divided by R divided by R plus J into or 1 by JXC, if I'm not wrong, 1 by JXC. So See, at some point, if you see that voltage is equal to the output voltage, means the output voltage at the resonant frequency, that means at x equal to x up, you will be having the value, you will be having that resonant range, and you can directly go for that FL will be equal to 1 by 2 pi RC. And with that, we can have that equation there. We will discuss this in detail. Right now, I don't have the material for that, so it's very hard for me to write here as well. So I'm moving on from here. I will give the proper material, or we will discuss about this equation, whatever we are seeing here. Yes, whatever equation we are seeing here, we will discuss about this equation in the next class if we want. Okay, right now you just notice this equation. This is A low. A low means the gain at the lower frequency, and the gain divided by the gain at the mid-range frequency will be equal to 1 by j, 1 by 1 minus j divided by into FL divided by F. Okay, F is the frequency of operation, and FL is at the resonant frequency of FL. Okay, so from that equation we will have A low is equal to A mid. I mean, you take the A mid to the numerator to the right hand side and substitute this equation, the above equation, in the equation number 1 here, so that we will be having such equation there. It is a very very elementary step. You can substitute by yourself, and finally on doing all those circuses, we will be having the term. We will be having the term FLF here, FLF here. So FLF is nothing but A mid, yeah, FL divided by 1 plus A mid into beta. That is the lower cutoff frequency after giving the feedback. FL is the lower cutoff frequency. You have a lower cutoff frequency and the upper cutoff frequency. I hope you remember that with respect to the characteristic of an RC coupled amplifier, and I mean the plot of that amplifier. Then only you will get a bandwidth. So FL is the lower cutoff frequency without feedback, and FLF is the lower cutoff frequency with the feedback. Okay. So now we are moving on to the upper cutoff frequency. So upper cutoff frequency will follow the low pass filter characteristic. Okay. We have already seen that. So in the low pass filter characteristic, we will be having a capacitor. Yeah, we will be taking the output across we will be tapping out the output across a capacitor. So the equation will be the exact opposite what we have seen in the previous section. It is the exact opposite. The only thing is we will be having A high, that is a higher I mean the gain at the higher frequency divided by gain at the mid-range frequency will be equal to 1 divided by 1 plus j into F by Fh. That in the previous case it was FL by F. Okay, I think someone is thinking. See, if you have any doubts, you can unmute yourself and talk to me better. Okay. Okay. Moving on. The same way we are solving this equation, so that we will be having F, the higher cutoff frequency. That means upper cutoff frequency FH of F will be equal to upper cutoff frequency of the amplifier without feedback into 1 plus A mid into beta. Here, if you see 1 plus A mid into beta is divided there, whereas here it is multiplied with that. So what does this mean is, you can clearly see that here this curve here is actually whatever you have done in lab. Okay, just keep that in mind. Okay, without feedback. Okay, and the second curve here is the response after introducing a feedback there. Okay, so the thing you can notice here is the gain is reduced, the gain is completely reduced, but the bandwidth is increased. So you are making a trade between the gain and the bandwidth. Okay. So say we what the gain says, see, take my gain out, give me some bandwidth. Okay. And what the bandwidth will say is, see, you take the bandwidth out, you give me the gain. Okay. So, but what we need is, we need higher bandwidth rather than the higher gain. Okay. So we are introducing a feedback there, and we are having a control over the bandwidth and the gain. Okay. Gain, we are trading the gain for bandwidth. Okay. There is a trade-off between them. If I want a larger bandwidth, I will introduce a feedback, but because of that, I want to sacrifice something. That sacrifice is actually the gain. You just check the gain of the red color curve here and the blue color curve here. Here the bandwidth is very high after introducing a feedback. That's why it is given as FLF and FHF. Whereas for the red curve, I mean the red curve that approximately I have drawn here, you can see that the gain is dependent on the lower frequency and the higher cutoff frequency. That is the bandwidth. Okay. And hope you know why this 0.707 A mid is there. It is because of the part 1 by root 2. 1 by root 2 is actually 0.707. Okay. And 20 log of 1 by root 2 is 3 dB, minus 3 dB. So from the topmost fellow, you move 3 dB below, so that you will be getting the bandwidth. Similarly, here you take the peak value, that means the mid-range frequency value, what is the corresponding gain, and you move 3 dB down, you will be getting the corresponding bandwidth of your amplifier. Okay, so you can see that bandwidth of this amplifier is BWF. BW means bandwidth of the amplifier with feedback. That's why we are having the suffix F. Whenever you see a suffix F, that means there is a feedback is there. Okay. Okay. This is actually known as, if you just check the values at every point, you take some point. I'm mentioning that with some other color. If I'm taking this point, if I'm taking some point randomly in my curve, and if I'm multiplying the corresponding gain and the corresponding frequency, that is actually known as the gain bandwidth product. That will be same in throughout the curve. Okay. So here, if I'm taking this point, I have a very high gain and a very low frequency. Okay. Whereas if I am taking it here at this point, if I am taking it here, or take this point, this would be better. If you check this, my gain is low, but my frequency is very high. Okay. So this is also a gain bandwidth product. If you see that this point, the product at this point and this point here, and the product at this point, the product of the gain and the bandwidth at this point will be the same, will remain the same. That is actually known as the gain bandwidth product. Okay. This is also true for your feedback amplifier. Okay. So this is what I wanted to discuss today, and there is a sum that has to be solved. I think you can take up this as an exercise, and I hope you can solve this now itself. I have the answer with me. Don't worry. For this question, I have the answer. In case if you are having some notes with you, you can definitely easily do this sum. This is a sum. For a better understanding, you can solve it by yourself. That is what I suggest. Okay, 1 minute. Yes. So far, any doubts? Because we are almost reached the end of the session. I mean, end of my part. What I have to explain, I have just reached the end of that. If you have any doubts, just text me. What is the doubt? From which slide you have the doubt? Yes, go on. See, please be frank, because it's very hard to see your face expressions, and in the real time class we will be accessing your uh, accessing you. What is the range of your understanding easily on seeing your face, but it's very hard from here, so I need your help to help you. Yes, any doubt? Someone please come up with a doubt. I need a doubt now. Don't say no doubt. I'm expecting someone to unmute themselves and ask for a doubt. I don't know how many left the conversation by switching on your rainbow. Yes, anyone? Yes. Go on. Okay. Can you take up this sum? And can you solve it now? I have shared a sum there, right? So can you? I need some responses through text, please. Can you take up that sum and solve it, because it won't. It is not involving any rocket science expressions or something. Okay, you just want to substitute the values for the expression that we have derived so far. It's like whatever we did so far. I mean, in the electronic circuit. Yes, go on. Yes, hello. Arun Kartik. ஹலோ ஆச்சரியமா இருக்கு. ஓகே சரி, ஆச்சரியமா இருக்கு லைன்ல இருக்கிறது. சரி ரைட்டு.
ரெக்கார்டிங் பண்ணல
ஏதாவது
சார்.
டவுட் இருக்கா? ஏதாவது டவுட் இருக்கா?
இல்ல சார்.
புரிஞ்சா இல்லையா? சரி, நேத்து இதுல ஏதாவது டவுட் இருக்கா?
எதுவும் இல்ல சார்.
எதுவும் இல்லையா?
ஏதோ ஒரு டவுட்
சரி.
மெசேஜ்ல வந்திருக்குன்னு நினைக்கிறேன் சார். ஏதோ 9.8
9 பாயிண்ட்
மெசேஜ் இப்ப நோட்டிபிகேஷன்ல வந்துச்சு எனக்கு இல்ல கிளாஸ்.
யாருக்கு எந்த இதுல டவுட்? Who is having the doubt?
9.6 ஆன்சர்னு நினைக்கிறேன் சார்.
Yes, speak out.
இல்ல சார், வோல்டேஜ் கெயின் வித் ஃபீட்பேக் ஆன்சர் சொல்லிருக்கேன்.
Which one? Yesterday's slide or today's one?
சார் யாரும் டவுட் கேட்கல சார், ஆன்சர் பண்ணிருக்காங்க.
ஓகே ஓகே ஓகே. இதுல ஆன்சர் பண்ணிருக்காங்களா? ஓகே, வெரி குட். எஸ் எஸ், வெரி குட் வெரி குட். ஓகே Okay, we will discuss the answers. Right? So I'm happy that you are responding. See, once you respond, only I could ask for something. அருண் கார்த்தி கொஞ்சம் இதுல போட்டிருப்பேன், மியூட்ல போட்டிருப்பேன். Okay. So see, these table values are the amplifier parameters. So amplifier parameters, that is the amplifier without feedback. Those amplifier parameters are given by voltage gain is 300. 300 is 300. Okay, and distortion is 4%. Lower cutoff frequency is 1 kilohertz. If you take that amplifier and if you do the frequency analysis, I mean, whatever you have done with the RC coupled amplifier, if you do that, the lower cutoff frequency is 1 kilohertz and the upper cutoff frequency is around 250 kilohertz. Okay, and the input impedance is 20 kilo ohms and the output impedance is also 20 kilo ohms. So what happens after introducing the feedback? What happens to these parameters after introducing the feedback? That is the question actually. Okay, so that for that we are taking, I mean, for 10% feedback, that means the feedback factor is 0.1 here. You can see that it is 0.1 here. So the things we have to calculate are voltage gain with feedback. That is very straightforward. You just have to apply that formula. AF is equal to A divided by 1 plus A beta. That's it. Okay. And sensitivity, bandwidth with and without feedback. Bandwidth with the feedback, you can easily directly get it. Without feedback, you can directly get it from that, just upper cutoff frequency minus the lower cutoff frequency. Whereas with the feedback, you want to find. Okay, input and output impedance with the feedback. Okay, with feedback, what are all the how these parameters will be? That is the actual example. That is the actual aim of this example. Okay. Okay. Now we will discuss the answer one by one. First, the voltage gain. Okay, AF is equal to A plus A by 1 plus A beta. You just take down these values and check whether we are doing the right thing, because I might have done some mistake. If there is a mistake, just let me know. Okay. AF is equal to A divided by 1 plus A beta. The value of A is 300 and beta is 0.1. That is the feedback ratio. And you have answered it correctly. It is 9.67. Your gain is 9.67. From 300 on without the feedback, your gain is 300. But with the feedback, your gain is dropped down to 9.67. From 300, your gain is dropped to 9.61. Why we want to then do the amplification? Okay, but I require only 9% of amplification only. But I want some other advantages from this negative feedback. That's why I'm going for the feedback circuit. Okay. Okay. Now the next point. Feedback loop gain. Loop gain is straightforward. Minus A into beta. I mean, this might not be there in your question, but we are just discussing. Okay. Loop gain is minus 300 into which is equal to minus 30. Okay. Noise with feedback, that means distortion is 4%. Correct. So that 4% we will be seeing that, see, your distortion will be also reduced by a factor of 1 by 1 plus A beta. So my noise without feedback is 4%. 4%. So I am substituting the 4% in the place of noise without feedback. So now my noise with feedback is 0.129%. Look at the difference with the distortion. Without using feedback is 4%, but I'm using amplifier, it's around 0.129. Distortion is very bad for an amplifier. Okay, so we have drastically reduced that from 4% to 0.129 by introducing a feedback. That's what we have to observe here. And sensitivity with feedback. Sensitivity, we have derived this. We have already derived this. We have already talked about this distortion with feedback. That means noise distortion and nonlinear distortion and frequency distortion. These things are we have discussed, but very in a very brief way. But sensitivity we have discussed. Sensitivity with feedback we have discussed. We have derived that actually. So we have the sensitivity equation like DAF divided by AF. That is the fractional change in the gain with respect to the with the amplifier with the feedback, and this is the fractional change in amplification without feedback. Okay, that sensitivity is given by 1 plus 1 by a beta, so that we will be having the sensitivity as 0.03. So you can see the sensitivity is very low. Correct, the sensitivity is very low after introducing the feedback. That is what this value actually you have to infer from this value, because it is very 0.03. Okay, and finally the lower and the higher cutoff frequency. Hope uh, these expressions we have already derived. You can directly substitute this in the place of FL. You will be having one kilohertz there, and in the place of A mid is nothing but whatever the voltage gain we have. Okay, that means the mid range frequency gain. A means gain, mid means mid range frequency. The gain at the mid range frequency is 300. Beta is the feedback ratio 0.1, and you directly substitute that in this expression, in this particular expression. You can easily find the lower cutoff frequency as 32.2. That means previously your lower cutoff frequency is 1 kilohertz. Remember, previously your lower cutoff frequency is 1 kilohertz. That's why we have wrote as 1 e power e3 means 1 into 10 power 3. Okay, so it is 1 kilohertz. After introducing because of the feedback, my lower cutoff frequency is reduced to 32.2 hertz. Okay, so this is the effect of feedback. And for upper cutoff frequency, that means upper cutoff frequency, previously it was 251 kilohertz. 251 kilohertz. Now, if you check after introducing a feedback, it is going up to 7.75 megahertz. That means from 10 power 3 hertz, that is in some kilohertz, we are moving on to megahertz range. So just look at the difference between the bandwidth of the amplifier before introducing the feedback and after introducing the feedback. Okay, that is what this particular sum tries to convey. That means this will add meaning to whatever things we have discussed so far. Okay, fine. Now we are going for the bandwidth. The bandwidth is nothing but upper cutoff frequency minus the lower cutoff frequency. So this is the bandwidth for a normal amplifier. That means without any distortion, I mean without any feedback. And this is the bandwidth of the amplifier with feedback. That is around 7.74 megahertz. Look at the difference. This is 250 kilohertz. If I convert this to megahertz, it will be 0.25 megahertz. Whereas 0.25 from 0.25 megahertz, we are moving up to, we are expanding our bandwidth up to 7.74 megahertz. So this is the kind of advantage we are getting from the feedback. Okay, and the very important thing is input and the output impedance. I think the initial itself we have solved this. This is the input impedance with feedback. You can clearly see that it is straightforward zeta into beta a plus 1. So here, for in the place of the input impedance, you can substitute 20 kilo ohms as given in your question, and this input impedance is now raised up to 620 kilo ohms. That means my purpose is served, because on introducing the feedback, my input impedance has to increase. So from 20 kilo ohms, it is increasing up to 620 kilo ohms. Just think of that. Okay, and my output impedance will be output impedance ZOF or ROF, anything would be fine. Okay, it is reducing to 9.6 ohms. Okay, just think about it. Your R0 is actually in the question, the R0 I have given is 20 kilo ohms. It is not 20 kilo ohms, it's just 300. Okay, just change that to 300 ohms. Okay, and the R0 is 300 ohms. From 300 ohms, we are reducing our output impedance to 9.6 ohms. Okay, this is the value of input and the output impedance after introducing the feedback. You can just make the comparison easily. So I end my lecture here. The only thing is, this output impedance is 300 ohms. Yes. Very good, Pragati. Yes. Very good. Prithvi Bata. Yes, very good. 620 kilo ohms. I think we have solved it. Output impedance. Please make sure your output impedance is 300 ohms for that amplifier. Okay. I mentioned that it's 20 kilo ohms previously, but it is actually 300 ohms. There is a mistake in the question. Please change that. Okay. Fine. Okay. So you must have got a idea, if not in the theoretical part, at least in the example part, you must have got some idea of how the input impedance, output impedance, how the bandwidth, how the distortion is getting varied or introduced in the feedback. I'm sure about that. And now your session is open for questions. Please unmute yourself and ask whatever you want. I will be very happy to hear your questions. Yes, go on. Yes, Pragati? Okay. See, I'm not leaving here without a question. For that sake, at least you want to ask a question. Come on, go on. Yes. Okay. I'll wait for 2 more minutes. Meanwhile, I will send you the material to you. Okay. I'm ending my session here. Thank you for your patience. And you can save your mobile charge or your laptop charge now. Okay. Thank you.